right? Now, today, we went through impedance matching. We went through using stubs, basically either open or shorted stubs, and either inductors or capacitors, right? I'm going to just redo one thing with y'all. I want to do this to make sure everybody's clear on this. And it really comes down to one thing. I'm just going to make up a problem. We're going to do it. We're going to do it with a stub, and then we're going to do it with an actual component. All right, everybody? And this should answer any questions you have. So for my problem, I'm going to have a load impedance equal to, say, 50 minus J30, and I'm going to have a characteristic impedance, Z0, equal to 50. So the very first thing we do is get ZL, and that's simply normalize ZL, capital ZL divided by Z0. That's the first step. So that's going to be 1 minus J 0.6. Does everybody see that, class? Right? I got to pull you guys. I've got to do something here because this doesn't automatically resize the screen so I can see. And if you can't put your cameras on. Now, everybody's got that, right? I mean, thumbs up, something to indicate you understand. All right, next, you got to locate it on this Smith chart. So where I have 1 minus J.6, this is an interesting one, by the way. Where is that? Well, this is the one circle, right? Correct? I mean, oh, sorry. I'm assuming you can see this. This is the one circle. Correct, class? It's this one right here that goes through the origin, correct? I mean, the center. Everybody see that? Now, where is minus J.6? Well, this is J.6. It would be minus, correct? That would be minus J.6, and where it intersects is right here, right? Do you all agree with that? Now, that would be your first point. That's ZL, right? Now, depending on how we want to do impedance matching, will give us different points to connect the actual, either the series or parallel shunted stub. So first thing I'm going to mention is this point here is 1 minus J 0.6. Does anybody see something odd about that? Is there anything that jumps off the page at you? Well, there's one standard thing. If we're going to do matching, impedance or admittance matching, we always want to move to the one circle, correct, class? Am I not already at the one circle? Can you all see I have a 1 plus or 1 minus J.6, correct? So for this particular problem, this is when on finals you get a lot. On this particular problem, if I was doing impedance matching with an element, I wouldn't need to move from the load. The only thing I would do, and I'll just put it right here, I would have my load here, and I wouldn't have to move at all. I would simply put something next to it that would, not next to it, in series with it. This would be impedance matching with a series element, where this added thing would get rid of the minus J.6. So it would be plus 0, or really this would have the value of plus J 0.6, and it would be a normalized impedance. Do y'all see that, class? How many? Just show hands. I need to try to get an idea if you're understanding this. All right. Now, what element has a plus J sense to it for the impedance, class?
Inductor.
An inductor. So that means this value of J.6, I'm assuming you can see it, well, would be equal to a normalized inductive impedance. Well, an inductor has an impedance of J omega L, right? That's the impedance of an inductor. To normalize it, we divide it by Z0, right? You're going to have to use the characteristic impedance on this one all the time. And that would be set equal to J 0.6. And that means L for this one irregardless of what omega and what Z naught is, would be 0.6, right? Remember, I'm after L times Z naught, right? And divided by omega. And that would be the value of the inductor if we were going to do a series element. Do you all agree with that, class? Now, I could also move a half wavelength. I could go, and I'm going to do this now. I could draw a radius. I mean, if you can do this with me, get a fresh Smith chart, it'll probably help you. I'm going to go from the center. I'm going to take my compass, and I hope you guys got good compasses because it'll make a big difference. And then you go around like this. And then get your straight edge. And I have drafting tools, so I'm fortunate. And then take your straight edge, and I'll move it up so you can see it. And the only thing I'm doing now is I'm drawing a line straight through the center of that circle, out the other side. Now remember, this is ZL, right? What is this point right here? Anybody? This is the normalized impedance. What is that point? Anyone? Help me out, guys.
The normalized admittance.
Yeah, make sure you say that and you understand. This is the normalized admittance. This is YL, and it's simply equal to 1 over ZL. Now, you can just take your calculator and take 1 over that, or you can look and try to estimate what that value is. If I take my calculator, I'm going to try to take my calculator at least right here. And I go down and I say, I'll call ZL equal to 1 minus 1J times 0.6. Then I get YL equal to 1 over ZL. And that is equal to 0.735. So that's equal to 0.735 plus J, 0.441. Right? And that's this point here. So this would be 0.1 if you were doing this. This is 0.2. Now, if we didn't want to use a series element, if we wanted to use a shunt element, do y'all follow me on this, class? For series, we just put it right next to, right in series with the load. You don't have any movement to do. But if you want to, you could move a half wavelength away from here, down here, and insert this too. It would work because every half wavelength you move is just like being at the load. Do you follow me? Every half wavelength. You could do that too if you didn't want to insert it right in front of the load, but just as well in front of the load. Now, for this one, how far do I have to move before and I'm going to go ahead and get a mile marker here. If you look on yours, do you get about 0.01 here? 0.1 lambda for the outer point. Take a look in your Smith charts. Make sure you see what I'm doing here. You see that, class? Show of hands, how many see that point on your Smith chart that you have? Y'all see it? Give me some indication if you do or don't. I'm really looking at faces. It helps me teach when I know you've comprehended. John, you see it? All right, everybody, I'm assuming you got it, right? Now, that point right here, that's the value of YL. Remember, if we put things in shunt or parallel, we work in the admittance domain, correct, class? Now, we have to move from there, and we can move to 2 points. Here's where it intersects the one circle. There's the one circle right here. That's one of the points, right? Or I can move to the conjugate point, and that's right here, correct? That's literally where we started from, correct, class? All right, now I want you to see this. We come from here, we go here, that's YL, right? Now just watch this. If I move from here to this point, how far did I move? Anyone? If I start here and I end up here, can you?
One quarter lambda.
Quarter wavelength, it's half around the circle or a quarter lambda, right, class? And then we could insert the value of the component right here. And this is 1 minus J.6. So you would want to insert a shunt admittance that would have plus J1.6. Do you agree with me? Everybody with me on this? All right. So what I'm going to do is this. I'm going to go from here. That's where the load is. That's the admittance, normalized admittance, to here. So in this case, and I'm going to show it here, I would take that normalized load, which is 1 minus J 0.6. That's my actual normalized load. And now I'd move exactly lambda over 4, a quarter wavelength away. And now in parallel, I would insert something that would have a value of J 0.6, right? Correct, class? That's an admittance. All right. Now, what has a value of J 0.6? Anyone? What has a positive sense for the admittance? Or let me ask you this, what has a negative J sense for reactance? Go ahead and say it. It's a capacitor, right? So the way you can think about this, if you're not real familiar with a capacitor, the capacitive reactance is 1 over J omega C. Isn't that right? Now, if you normalize it, you would divide it by Z naught, right? So if this is divided by Z naught, now that's the normalized capacitive reactance, right? Everybody see that? When I take 1 over that, that would be the normalized capacitive impedance or admittance. I'm sorry, admittance, right? So 1 over this, or simply J omega C Z naught. That's the normalized admittance of the capacitor. Do we all get that, class? Right? Ben, can you see this okay? I mean, when I see people looking, and I'm trying to get a read on you guys so I can teach most effectively, but I'm assuming you all see this, right? That's the normalized capacitive admittance, and that has to be equal to this minus, or it has to be equal to J 0.6. So when we add them together, they cancel. So this is equal to J 0.6. Do you all follow me on this, class? Because admittances add just like resistors in series, admittances in parallel add. Correct, class? And what would the value of this capacitor be? Well, it would be 0.6 over, right, over omega Z naught. So whatever the value of Z naught and omega are, that would, if we divide that into 0.6, we would get the value of capacitance. And that would be placed in parallel a quarter of a wavelength away. Am I clear on that, everyone? Now, how many see that? Now, if I said you had to use an inductor, if I said that, if I qualified that and I made you use an inductor, then I'm going back to the Smith chart. And I'm going to say an inductor in parallel too, or in shunt. Follow me? So it's not in series, it's in parallel. Listen carefully. If I said that, then that means you would move to this point from here to here. Do you all see that? We're going to do this with an inductor next. We just did it with a capacitor. We did it first with a series element, right? We did it with an element in series, and it was an inductor right here. That was in, go ahead.
I have a question.
Can't hear you.
I have a question.
Go ahead.
So kind of the roles for capacitors and inductors are reversed when we go in admittance.
They're 1 over, right? Admittance is always 1 over impedance.
Right. So like if we're going in series and we want to put a capacitor in, we look for the 1 plus J something.
Well, hold on for a second. If you're doing anything in series, you're doing it in the normalized impedance domain. If you're putting anything in parallel or shunt, it's the normalized admittance domain. Those are the 2 key things.
Right.
And a capacitor will always have a positive admittance sense in J and a negative J impedance sense. So opposite for the inductor, but those are things that are fairly obvious. Now, follow me on this. We started here, we put one right at the load, an inductor to do impedance. We're going to get a 0 reflection coefficient here because the normalized impedance will just be 1 after we do this. This is using an inductor in series. That inductor could have been placed a half wavelength away. Now, The next thing is we used an element in shunt that was a capacitor. So we were into YL and we moved to this point. That was with a capacitor, right? If I said you had to use an inductor in parallel, and by the way, this is not rare, this is not usually done because an inductor at DC is a short circuit. And if there's any DC voltage that's developed across the line, it's just, say, a voltage from a gate or something like that that's left open, then it would short that out and the circuit wouldn't function. But if you were forced to use an inductor in parallel or shunt, now you would move to this point. And you know why? Because this is going to have a plus J sense, right? You see, that's going to be, this point is 1 plus J something. Do you all see that? This point is 1 minus J something, right? Now, what's this point actually right there? That's on the one, well, I'm sorry. Yeah, that's on the one circuit. It would be 1 plus J 0.6. It would be the conjugate of this point, wouldn't it, class? Right? Y'all see what I'm doing? All right, so how far do I have to move? Here I have to take my drawing triangle or straight edge, and now I go from the very center, and I hope you can see this. I do that, and I run it right through that point, if I can. And I got to flare the line and see what you get out here. I'm getting something just shy of 0.15. I'll call it 0.148, 0.148 lambda. Take a look at that. Do you get about that? Everybody, can you all see that? And you have to have a good compass to do these problems effectively. All right, now how far did I move? I moved from here, right? That was the start to here. So really, I moved, this is 0.148 lambda, this is 0.1 lambda. I moved the total distance of 0.048 lambda, right? This distance right here would be 0.48 lambda to here. Y'all agree with that? Can you all see that, class? Give me a thumbs up if you see it. I gotta make sure. All right. Now we're going to calculate the value of that inductor, right? This is an inductor in parallel. So I'll draw it over here. We would have this. This is another way of accomplishing impedance matching. Here's my load, ZL. And I'm not even, and I know it's normalized. ZL is simply 1 minus J 0.6. Now I move a total distance of 0.048 lambda. And now I'm going to attach an inductor in parallel with that. I'm going to calculate the value. So how do you calculate the value? This is how I always do these problems. And I tell you one thing, if you become creatures of habit where you do the thing the same way, you make less mistakes than if you go at this in different ways and forms. So the first thing I do is say, what is the impedance of an inductor? Well, it's J omega L. I think we all agree with that, right? The impedance of an inductor is J omega L, correct? Now, the next thing I have to do is normalize, and I always do this. Now I normalize it. Now I have the normalized impedance of the inductor. Everybody with me? Now, when I take 1 over that, I have the normalized admittance. So the normalized admittance would be minus J times Z naught over omega L, right? Now that has to be equal in magnitude to the value of, if you look here, I get a value for this one right here of 1 plus J 0.6. So it has to be equal in magnitude to J or to 0.6, right? Does everybody follow me on that? Because when we add this thing together, the admittances, they are going to get rid of that imaginary component. I'm left with just a real part, 1, right? That's the goal of impedance matching always. So I set this equal to minus J 0.6. And I can see that now my L value would be what? It would be Z naught, correct? Divided by omega, right? And then 0.6. Do you all see this, class? I want you to take a look, make sure you follow me. All right, now let me recap what I've done. I've guessed the point. I mean, I guess the load, and I've done matchings. This is getting zero reflection coefficient. Really, we're doing impedance matching by either putting an inductor or a capacitor in series or an inductor or capacitor in parallel. Do you all follow me on that? I've covered every possibility of using an element to do impedance matching with either an inductor or a capacitor. Does everybody agree with that? Now we're going to do it with stubs, and the stubs will simply replace the elements. They're going to act like either, if they're in parallel, they're going to act like either the inductor or the capacitor in parallel. So I'm going to get a fresh Smith chart to do them with the stub. And I'm going to use the same values. I know the load I had was 1 minus J.6. So let me just draw that out there right now. And I'll tell you something, class. I got to send one email. If you can go ahead and replicate the load impedance is 1 minus J.6, but I got to send one email because I can't be at a meeting at 9 o'clock and I haven't one. So bear with me. I know I'm going to get asked some stuff at this meeting. Wait. No, I take it back. I don't have that one today. Thank God. It popped up, but I don't have that one. Never mind. They canceled it, I think, or at least maybe they didn't even schedule it. So 1 minus J.6 is, this is 0.6. This is the first point I came in at. This is ZL normalized, and that's 1 minus J 0.6. Now I'm going to take my compass. I'm using that Black Magic Smith chart, but if you have a different type, it's fine too. It just has to be something that's not distorted, because if you stretch them a little and make them elliptical instead of a perfect circle, they won't work. Then I take my straight edge, go right through the center. Something else I did, this pencil has got a very, this pen is a very fine point, dark pen I can use, and that's what I would like to see on Smith charts if you have to take pictures of them, because it'll show up. You all see that line fairly well, right? I'm talking about the line I drew here. Not, this is pencils. It's faint, but you all see that. Okay, that's 0.1, and always label the points. This is 0.2. That's YL. Now, I want you to listen. What I wanted to do, and I didn't put this as a requirement, but now I'm going to say make the stub a minimal length. And this is typical. So we're going to do impedance matching, but the requirement is, and it's going to be a short circuit stub, and it's a minimal length. So here's my load, ZL, right? Now I'm going to come down a line some distance. I don't know the distance. This has a characteristic impedance Z0. And I'm going to attach the stub to this point in the line. And the stub is going to have some length, L stub. And this is L through. I'm just going to call it THRU. Here I know this is 1 minus J 0.6 is the normalized impedance of that, right? Now listen, this is important. If I wanted the stub length to be minimal, and that's typically true for a reason. When we're talking about fabricating stub tuning like this, instead of using an element, you always think about the real estate you're going to need to do that. They talk about the footprint of your circuit a lot of times. So if you have a piece of silicon, and this is going to be fabbed on, say, using a coplanar line or something like this, something very small, where these chips are going to be small. If this line is long, it's using more of the actual surface area of the silicon. Make sense to everybody? You don't want that. Usually the stipulations they place on design is to have a minimal amount of space used and effectively do what the design's supposed to. So if they want this as a minimal length, I have to first take a look at over here. What does that mean? Well, if I have a short circuit stub, what is the impedance of a short? We're going to do it one more time. Anyone?
0.
0 ohms. If it's normalized, it's still 0, isn't it, class? You divide it by 0 by divide by anything is still 0. So the point you're coming in at is right here. This is the point 0 right there. Follow me? Everybody see that? I hope you can see it. Can you see it, class? Now, if that's the normalized load impedance of the stub, if it's a short, what's the normalized admittance? It's right here. And take a look on yours. It should be infinite. You see how it's going to an infinite value? Take a look on that. Can you all see that? That means the impedance of a short circuit, or the admittance of a short circuit is infinite. The admittance of a short is infinite. Now, when you start moving, you can see that the first values you get down here have a negative J sense. Do you all see this? Negative J, and when I'm saying the values, these are the values. The lines are perpendicular. You see that? It's like minus J, what is that? 0.03, 0.02, or I'm sorry, I can't read my own thing. I'm sorry, not 0.2, but this is like minus J 1.82, what is that? 2.23 minus J3. You all see this, class? And the closer I get to this point, the closer I get to an infinite value of impedance with a J sense to it. Can you all see that? So if I'm coming, when I start, this little bit of length will always be minus J. It means I want to match this. I want to put it in shunt with something that's got a plus J sense, so it'll annihilate it. Agreed, everyone? You follow me? So what's the plus J sense? Getting back to here. Well, here's my admittance. Remember, we're going to add this in shunt or parallel, so we work in the admittance domain. There's where I started. I want to get a plus J sense, so I'm going to get right to here, right? I'm going to get the point 1 plus J 0.6. This would minimize the length of the stub. Okay, and that's exactly what we did with another element before, right? That was a capacitor, right? We put a capacitor that distance away in parallel. Correct, class? If you remember. So what is this distance? Does anybody still remember it? Wasn't that 0.048 lambda? Y'all remember that? This is it's not exactly on mine, but it should be about 0.1 lambda, and this should be about 0.148. Y'all remember this, class? Take a look on your Smith chart. Just make sure you're following what I'm doing now. I'm not trying to go too fast. I want to make sure I cover this clearly. Everybody see that? All right. So this is J.6, right? When we move from here to here, we have 1 plus J.6. Now, if we add minus J.6, we just have 1. That would be the normalized admittance. Well, 1 over that, or 1 over 1 is 1, would be the normalized impedance. And that means the actual impedance of that point in the transmission line would just be Z0, and the reflection coefficient would be 0. Do you follow me on the reasoning? Why we're doing what we're doing? So I've got to get rid of this. How far do I go down here to get rid of that? Can you all see it? Where should I stop? Tell me.
Can you move the Smith chart up?
Oh, I'm so sorry.
Thank you.
What I was saying is, where do I stop? Just look. Tell me where to stop. I'm at point. I've got 2, 1.8, 1 minus J 1.2, minus J 1, minus J right here. Correct, class? That's 0.6 or minus J 0.6. This is the point minus J 0.6. Can you all see that on your Smith charts, first of all? All right. Now what you have to do, Carlin, can you see this okay? I can't tell if you could or not. Yes?
Yeah, I was just trying to make sure I was looking at it right.
Yeah, you should see 0.6. That line comes in, and it comes in perpendicular to the actual outer circle, and it should have a marker on your Smith chart of 0.6. Now, You know, we got black magic Smith charts. There's a variety of different Smith charts. Some of you may have printed things off from the internet that are better in some respect. They're, you know, a larger, or they're more clear, finely resolved. No matter what Smith chart you use, you have to be able to find that point. And that's what I'm getting at. How many are using black magic Smith chart? Anybody? This is a black magic Smith chart. But I mean, there's many others that have, I guess, some unnamed that are available on the internet. If you just do Smith chart and you look at the images, you'll see a ton of them. Pick the one you like, just make sure it has the proper notation, because sometimes instead of an impedance Smith chart, what they give you is an admittance Smith chart. It kind of drives you nuts. It's backwards. All right. Now, how far did I move from here to here? Anybody? What's this point in wavelengths towards generator? Just tell me. Can you tell me? That point right there is at 0.25.
2.5.
Yeah. I'm trying to get you people to interact. It helps me, I think, and it helps you too, hopefully. All right, so what's this point out here? Now, this is important. Take your straight edge, all right, your straight edge, and go from the center of the circle like I'm doing. Put your pen there, and they go right through 0.6, which is about there, and draw a straight line. You're going to get a little bit of difference from me, and then boom, it comes out. You see what I've done? I went right through that minus points, J.6. Flip it up here, and then I always look at things so I can read the numerals normally. They're not upside down. So if I look here, I got 0.412, 0.414. So this looks like about 0.414 lambda. Do you agree with me? You get about that? And I'll tell you one thing, as I get older, the magnification on my reading glasses gets large, and I wish I had some that were a little more magnified, because even that becomes a little straining on my eyes. Now, how far did I actually move? Well, because I'm adding a short circuit stub, my stub length would be what here? It would be 0.414, right? Minus 0.25, and that would be in terms of wavelengths. That would be the length of the stub, right? And what was the length of the through line from here to here? 0.048 lambda, right? I'm going to tell you one other thing about this. So this is 0.048 lambda. Are you with me? I want you to just take a look at this. Make sure you understand everything I did. And Ben, are you recording this? Yes?
Yes, I am.
All right. Has anybody looked at any of the videos in the past couple of lectures or anything? Anybody?
I looked at some of the beginning ones and they worked, but I haven't looked for a while.
All right. What I need to know is if anything is wrong about them or unclear, let me know, and then we'll remedy the situation. Now, you can upload these things on YouTube, or is that where you're putting them, Ben?
I've been putting them on YouTube.
YouTube is the best. It's a stable platform. They'll be there forever. They don't go away. I don't even know if you can take stuff down from YouTube. I've never tried that. I've got lectures that are 10, 12 years old. They're there. It's permanent. It's fantastic. So, and I don't mind the whole world looking at these things if they want, because frankly, this is stuff that there are so many lectures on Smith charts and transmission lines out there. Mine is just inconsequential. Now that's with a shunt stub. I mean, with a short circuit shunt stub, right? Here's a question for you. How would this change? By the way, what is this value? Can anybody tell me?
0.164.
0.164, did you say? 164 lambda, correct? Is that right, Carla? Did you say that? Yeah, okay. We've got the values now. Normally, remember, when they do designs, you don't measure things in wavelengths. You measure things in meters, centimeters, millimeters, things like that, nanometers, microns. So, and on the next quiz or test that you get on Smith charts, I'll ask these dimensions in wavelengths. And how do you always get wavelength? Well, wavelength in general, wavelength will always be the velocity, phase velocity on the line divided by frequency. I think you remember that from physics, right? It's really 2 pi over beta, right? But don't, like beta times the wavelength is 2 pi radians, but this is the way it's usually rendered. Now, phase velocity on transmission line, and I want to tell you this, is usually given as the speed of light, but not always. And here's the way it's typically given, because when you have a dielectric between two conductors, that dielectric can have an epsilon relative greater than 1, and that will slow things down. Now, I'm going to just put this down here for you. Normally, the way they write wavelength is going to be c, which is 3 times 10 to the 8th. Then they'll divide that by the square root of epsilon relative. You'll see this in books all over the place. And then they'll divide it by frequency, and they'll say that, in fact, would be the wavelength. Now, wavelength can be meters, it can be millimeters, whatever it is. But then all these dimensions would be, like this dimension would be 0.164 times the wavelength. And if the wavelength was like 10 meters, then it would be 1.64 meters, which is an immense distance when we talk about microelectronic parts. But typically, these dimensions are of the order of centimeters or less when you do chip design. I'm just trying to tell you the facts. Now, how many know what FR4 board is, that green board that's used to like as a circuit board for a lot of components? Did you all see this? You ever tear something apart, like rip an old router apart or something like this? That's called FR4 board. That's used for this type of stuff. You can have coplanar lines and stuff like this. How many know what a Duroid board is, or high frequency RF board, laminates? Anybody? If you haven't worked with it, you don't really. All right, what you're going to be exposed to is a lot of different boards that are used to delineate or pattern things that will be transmission lines and stuff like this that they'll mount literal chips on. Now, I can't show that to you right now, but I will later, hopefully. But remember this one thing when you're doing a design. The people that delineate these things do not want things in lambda. They don't. They want it in meters, centimeters, or millimeters. And usually they hate inches. They want it specified in the MKS system or System International. Because here's what this happened to me one time, and I don't want to spend time here talking about the whole story. But when you ship off a design, and you're going to do this at some point, you're all about ready to get into some design work. And in the next 5 years, you'll probably, at least some of you will encounter this problem. When you send out a design to be fabricated, you're going to specify dimensions. If you just put 0.164, the default thing in that guy's mind is probably centimeters, and he'll assume that. So he's assuming that fact. You have to make sure you put the units down, put either millimeters, centimeters, or something like this, because with designs like that, if you ship this stuff off, and the people that do this usually are being paid by the hour, and they don't have a real vested interest to take a look and make sure it's right. They just fabricate something that comes back to you. Now, I had an antenna design built for me one time, and this was for NASA, and it was it was an antenna that had it was basically it had 3 elements at 120 degrees, and it had multiple antennas on each one of these elements, and it was connected at the center and the back with a coaxial cable. And I did the design and theoretical stuff. Well, some of the things I didn't do was put the dimensions down in meters. All right, I put the dimensions down. I really, so long ago, I don't remember if it was in inches or in feet or whatever, but something else. The other thing I didn't do was I didn't get a good look and inspect the design before it was sent back and then measured at Ball Aerospace. So the technicians build these things. And remember this, technicians that build these things don't have a vested interest. They get paid by the hour, all right? Well, when they measured something called the standing wave ratio on the back of the thing, it was ridiculously high. It was 4. That means it's a very bad design. And I couldn't understand for the life of me how this could happen. Well, one of the technicians, when he's soldering these things, left a big solder ball on the back side of the coax cable connector. A solder ball at the frequencies we were using, about 1.4 gigahertz, or 1.414 gigahertz, is a massive inductor, and it looked like an inductive impedance, and therefore it messed up everything. Luckily, there was a guy who was an engineer out there that was available to take a look at the antenna during the test, and he flipped it over and he said, "What's this horribly large solder ball there?" And he removed it, and the thing worked. But still, I'm going to tell you, this is my piece of advice for this Friday. Never assume they understand. Always assume they don't understand. Put the exact dimensions down and always ask to get pictures of the thing that they fab so you can inspect them. Because I'm telling you from experience now, your boss, when you do a design, he's going to assume you can do a design at some point. It's going to be shipped off, and it comes back, and if it doesn't work, it's your head that's going to roll, not that technician's. You're responsible. I'm telling you this. I looked like an idiot in front of those guys at NASA. Luckily, this guy figured out what was wrong. All right, we did that's the shunt stub, but if it was, say that for whatever reason they say, we can't put a short there for some reason. We can only use an open circuit stub. How much longer would that be for an open circuit? Can you guys get it just by thinking about it? If that's a short circuit, right? If we wanted an open circuit, how much further would we have to go if we wanted to make it an open circuit? Can anybody get this one? Take a guess. All right. With a short circuit, I start here, don't I? Right? Short circuit stubs that are short for admittance matching or impedance matching. Well, an open circuit would start right there. You all see that? How much further is that from here to here? Class?
0.25.
Right, a quarter wavelength longer. So the only thing you would do is that if you know this stub length is 0.164, you would add 0.25 to that if it was open stub. You all see that? And that's sort of stub tuning in a nutshell. Almost all stub tuning, almost all, is done in parallel.
Professor.
Yeah.
Can we also go to the other intersection point?
Yep.
And we have to go up to the top point, so it's not as far?
Yeah, that's right. If we had an open circuit stub and we wanted the shortest length, we would go to this point. Follow me? And that point is the conjugate of this. So I'm looking at about 0.148. So we'd start at 0 to 0.148. We'd move 0.148 lambda to get to that point. All right. Can you all see what I'm doing here, class? Show of hands, somebody got that. Now that's basically stub tuning in every way, shape, and form possible. Either series or shunt. Just for the record, almost all stub tuning that I'm aware of using a transmission line is done with a short circuit stub in parallel. Almost all. Remember that, short circuit stub in parallel. Almost all impedance matching done with elements is the preferential way is always with a capacitor. And it doesn't matter if the capacitor is in parallel or series, but usually the capacitor is in parallel for a reason. A lot of the times transmission lines have a DC voltage that they need to maintain. And if you could put a capacitor in series, it'll block DC. So they put it in parallel. You hear me on this? And this is just practical insight from all the stuff I've done in my life. And there may be exceptions, but that's generally true. And one last thing, in general, we shun from using inductors, right? And there's a primary reason for it, because inductors, generally, when you got current running through an inductor, it has a magnetic field around it that can, the magnetic and electric field that will be caused by the time varying magnetic, influence other electronic components. Inductors are by nature evil in terms of their electromagnetic interference. It causes a lot of problems with interference. And you know what interference is, right? You throw on a hairdryer or something and your radio, AM radio clicks. That's interference. That's an unwanted effect. So we shun inductors generally. And I'm telling you from practical design, There's always an exception when you have to use them, trust me. But in general, we shun them, or we make sure that they're not going to influence any devices. We'll shield them. All right, I'm going to tell you where we're going. I know my time is up, and I didn't get to do the solution to the quiz next time real quick, but I want to tell you where we're going so you can read about this weekend. I appreciate you all staying with me. We're done with that Smith chart stuff. We're going to this. And this is an easy one to understand, but I'm going to take you through it. This is on page 87, and we're going to do transients. Now, transients are real important. So what is a transient? It's basically taking a transmission line like this and just flipping a switch. Put 4 volts there, I flip a switch. Well, you can almost imagine what happens. There's the initial wave going to go down with the speed of light, hit here, and some of it's reflected and some of it's absorbed. Then it's going to come back, hit here, and some of that wave is going to reflect, and bang, 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 bang. And basically, the thing's going to keep reflecting back and forth until it comes to a steady state. Does that make sense to everybody? Right. Well, we're going to cover that, but I can tell you 2 things that are important right off the bat. Once that switch is closed, after a long time goes by, the voltage on this load will be as if this transmission line isn't there. Because if you think about this, a transmission line is 2 perfect conductors generally, right? As time goes by, as time goes to infinity, they look just like good conductors. So it's like that 125 ohms is just stuck right there at the beginning, and the transmission line doesn't exist. So the voltage, as time goes to infinity, will just be found through voltage division. You would take 4 times 125 over 150, the source resistance plus the load. That's what it is as time goes to infinity. The instant that this first wave comes down there and strikes this, the way you get that is you make this look like just Z naught, 75 ohms, and then you find the amount of signal that would be on that 75 ohms when the switch clicks. So it'd be 75 over 100, because you can see there's 25 there, times 4. That's 3/4 of 4, 3 volts. So there would be 3 volts here moving at the speed of light, basically, or almost the speed of light, 0.1 C. And when it strikes here, you're going to get something called a reflection coefficient. So that part of the wave, the reflection coefficient, times the incident wave will move backwards. But I'm going to cover that next time. This is a fairly obvious thing. And if you could you read through the section on transients in the book, section 2.8. It's not hard to understand, but I want to take you through it Monday. And if you read it before I do it, it'll save me some time. It'll give you some preparation, all right? Now, I'm not going to give you any homework, but make sure you understand impedance matching well. And any questions you have on Monday, we'll take up on impedance matching. You guys pretty good with this now, with the impedance matching? Okay. And go through it with your mind. If you're using inductor or capacitor in series or parallel, 4 possible places, right? Think about where you'd locate them if you wanted to minimize the length from the load, say. Things like that. And then if you're going to do the same thing with stubs, where do you locate the stub and why? If you want a minimal distance on the stub. That's it in a nutshell. Okay, have a great, safe weekend.